Hi, I'm presenting our recent work on a simple method for complex in-hand manipulation. This is a joint work with Chen and Pulkit Agrawal. Let's consider this object reorientation task. This task is challenging because the action space is high dimensional and also there are frequent contacts between the objects and the fingers. And an even harder task would be if we flip the hand upside down. Due to the object gravity, the object can fall easily. So our work demonstrates the capability of reorienting more than 2,000 geometrically different objects without using any object shape information. The learned controller also generates two objects with novel shapes. We also demonstrate the ability with the hand facing upward and also the downward. Lastly, we also train policies that only use the observation data that can be readily available in the real world. Our method follows the teacher-student training pipeline. First, we train a teacher policy using the full state information. Note that we do not provide any object shape information. The policy is trained with PPO. Next, we train a student policy that uses only the observation data that can be available in the real world. For example, it can be a reduced state, including joint positions, object pose, and target orientation. Or it can use the vision input, such as the point cloud. This student policy is trained with Dagger to imitate the expert policy. We use two different data sets in our experiments. The first one is the EGAD dataset, which has over 2,000 geometrically diverse object meshes. And the second one is the YCB dataset. So given the objects with such diverse shapes, one might think that the object shape information will be critical for the reorientation. However, is that really the case? So to answer this question, we experimented with three scenarios. First, the hand face upward. Second, the hand faces downward, but there's a table below the hand. Third, the hand needs to reorient the object in the air. So the first case, we can see from these two videos, the hand can easily manipulate the objects without knowing with different shapes. And note that we do not provide any object shape information. We found that the hand reorient the objects by throwing the object into the air and with a spin and catch it precisely at the moment such that the orientation is matched. And our experiments also show that we can get high success rate by training and testing on the same data set. Moreover, we can also see that the policies get high success rate when it's transferred to the other untrained data set. And now let's move on to the hand facing downward case. This case is much difficult because the exploration is hard and the hand needs to overcome the object's gravity. And it's hard for the hand to figure out the shortcut way by throwing the objects in the air for reorientation. And in this more challenging task, one might think the object shape information should definitely matter here. So to see if this is really the case, we experiment with reorienting objects with external support first. And we can see from this video that model-free IO can effectively learn to make use of the table for the reorientation. And here are more videos. So the first one is reorienting the can and a toy gun and also a tree seed box. And last one is the EGAD dataset. So we can see that some interesting behaviors emerge from the training, such as it will pinch the object or pressing the object on one side to lift the object. And the last scenario we look at is to reorient the object in the air. For the sake of the time, we will skip the technical details, but only show the results here. We can see that the hand can slowly reorient the objects. Again, we want to emphasize that we do not provide any object shape information to the policy. Lastly, we also trained student policies that use raw vision input. To process the point cloud, we designed a sparse 3D convolutional network. And our network also has some recurrent network to better accumulate the information over time. Due to the large compute demand of rendering images and also policy training, we train one vision policy for each object. And this table shows that our vision policy can also achieve very high success rates with the hand facing upward. For more videos, please check out our website. Thank you.
Yeah, thanks, Tao. And any questions from the audience? This is a very interesting paper, actually.
Thank you.
I have a quick question. What's the action space of your model? That's the
It's the relative change in the target joint position.
The joint of the hand, all the joints, right?
Of the actuated joints. So the shadow hand has 20 actuated joints.
I see. Is there any case that it's not possible to render the objects to the target orientation?
Yes, there are some failure cases. So the success rate is not 100%, but it's still considerably high given the difficulty of the task.
Yeah, this task is very difficult, but I have maybe a general question for the robotics. Do you test in the real thing and this kind of things? And I saw you show a lot of, yes, in simulation.
Yes,
yeah.
So it's in our future work, and we have tried some experiments with domain randomization and show that the policy can still achieve high performance.
In the real thing. Yeah.
In the simulation with domain randomization, like adding noise to the observation or having different dynamics of the hands and objects.
But
we haven't tried the real world experiments yet.
Okay. Yeah, I see. I think, yeah, another question is a policy shared?
For different scenarios, we use, we train different policies for each scenario and for each data set.
Okay. Yeah, any questions from the audience? If no, I think we will conclude this session.